Alright gang, here we go. Physics, Unit 1, Part 3. We're going to talk about acceleration, velocity time graphs, kinematic equations, free fall. Alright, so pretty big stuff here. Alright, so right here at the beginning, we're trying to decide what a good definition is for acceleration. So we really are going to explore what the difference is between the physics terminology for acceleration versus the term that everybody else uses as their definition of acceleration. Okay, so we've got four situations, and we're going to decide which ones involve accelerations. All right. So we've got a car shortly after a stoplight turns green. So we've got a car, it's in a stoplight. You know, here's my car. This is my bestest car I've ever drawn. All right, and then we've got a green. All right, so the car starts going. Well, sure enough, it went from stopped to go. So therefore, yes, this car is undergoing acceleration. Okay, how about a car approaching a red light? So now you've got the same car. You know, he's just having a run of luck, and you know he hits a red light. Okay, and the red light's lit red. Okay, and so he's going to stop, so he's going to slow down. Now, most people outside of the physics world would say, no, that car is not accelerating, that car is decelerating. However, in physics, deceleration is not really the correct term. What we refer to it as negative acceleration. Okay, so that means our acceleration is actually in the negative direction, or opposite of our velocity direction. So that means we're actually slowing down. Yes, but that's still termed acceleration. Okay, so our car is actually accelerating here. Okay, because our velocity is changing. All right, how about a car with cruise control set at 80 kilometers? Well, here our velocity is not changing, so therefore this car is not accelerating. All right, our velocity is even. A car turning a curve at constant speed. Now this is interesting. Okay, so remember acceleration. Okay, acceleration is defined as the change of velocity over the change in time. Now remember, velocity is defined as the change in distance over the change in time, right? Okay. Now remember, or distance, not displacement, or distance. Not distance, displacement, the change in displacement over the change in time. So this tells us that if our displacement changes, our velocity changes, and if our so therefore if our displacement changes, our acceleration will also change, because they're all linked to one another. Delta x goes directly into v, and v goes directly into acceleration. All right. So if we change our direction, that also means that we're changing our velocity. Right? Because velocity tells us not only how fast we're going, but in what direction we're going. Okay, remember we talked about positive, negative, right? Positive, negative. Okay, so if our velocity changes direction, right? If we change direction by turning around in a circle, that means our velocity has changed. That means our acceleration has to have changed, which means we have to have accelerated. Okay, so therefore, this is also accelerating. Okay, so this gives us kind of a robust definition of acceleration. Acceleration is simply just any time you have a change in velocity. Anytime change velocity. All right. So here's our general formula for the average acceleration. Notice it looks very similar to the change in velocity formula, or the velocity average formula. Okay, so change in velocity over change in time equals VF minus VI. Remember, this little f means final and the I means initial. So VF, final velocity minus final initial, over final time versus initial time. Okay, and then we have average acceleration, okay, is equal to change in velocity over the time required for the change. So let's think about this for unit-wise for a second. Okay, what are the units for velocity? Well, generally, velocity is distance over time, but so let's just think about SI units for a second. So in SI units, the velocity is defined as meters per second, okay? And time is also second. So remember, if we divide by a number, that's like multiplying by its reciprocal, okay? So this is meters per second, or meters per second squared. So that's where we get the units for that. Okay, acceleration is the rate of change of velocity. There's your units. Now here's where things get interesting. If the acceleration of an object is 0, then there's two cases. We're moving at a constant velocity. It doesn't really tell us what direction we're moving, but it's constant velocity, or we're at rest, which in essence is also constant velocity, but the velocity just happens to be 0. Okay, so acceleration needs two parts. It needs a magnitude. Now, when you hear the term magnitude, what I want you to think of right away is the absolute value. All right. So when you think about magnitude, you should immediately think of absolute value, meaning how big your number is, how far away from 0 you are. Okay, so the magnitude just tells you how big it is. It doesn't tell you if it's positive or negative, but then the direction tells you the magnitude, or the positive or negative value. Okay, so we're going to look at this object, and it's moving with these values, generally positive or negative velocity or acceleration, and we're going to decide how our object is moving. Okay, so for this first one, our object has a positive velocity, so that tells us it's moving to the right or up. We're just going to stick with left and right for this example just to make life easier on ourselves. So the positive value here means that our object is moving right. Okay. Now, the acceleration right here means that our object is being pushed to the right. Okay. In other words, our velocity is moving to the right and our acceleration is moving to the right. So therefore, we should be moving to the right with increasing velocity, because the acceleration is going to make us getting faster and faster and faster and faster. All right, so in the second one, we've got an object that's moving to the right. We know that because the velocity is positive. Okay, so we're going to the right, but our acceleration is negative. Okay, so that means that our acceleration is in the opposite direction of our velocity. So if our object is moving to the right, that means our acceleration is moving to the left and pushing against our object. Now, at this specific moment in time, the object is moving to the right. We know that because its velocity is positive. Eventually, the velocity of the object will reach 0 and it'll start going backwards. Okay, but right now, at this specific moment in time, because the velocity is positive, that means he's going to the right. So our object is moving to the right and it's slowing down. Okay, now in the third one, our velocity is moving to the left. Okay, we know that because it's negative, so we're going this way with our velocity, and our acceleration is also going to the left. So that means it's going to be reinforcing our velocity. So it's very similar to the first example, except now it's opposite. Instead of going to the right and being reinforced to the right, we're going to the left and reinforced to the left. Okay, so we're moving to the left and speeding up as we go that direction. Finally, our object is going to the left, okay, and our acceleration is going to the right, so it's going this way. So at this specific moment in time, our object is going to the left, and we know that because the velocity is negative, but we are slowing down because our acceleration is in the opposite direction of the velocity. So we're moving to the left and we're slowing down as we do it. All right. Now find the acceleration of an amusement park ride that falls from rest to a velocity of 28 meters per second downward in 3 seconds. Okay. So we're finding the acceleration when we know acceleration is equal to the change in velocity over the change in time. Okay. Velocity change in anything is always final minus initial. So we have velocity final minus velocity initial over time final minus time initial. Okay, so the final velocity is equal to 28. It says right there, so we put 28 here. But now let's think about this. All right, so we've got an amusement park ride, and it says that it falls from rest. So what is our 28 value? Well, it has to be negative because we're falling. Remember, we defined in this unit that right and up is positive and down and left is negative. Okay, so because we're going down, it has to be a negative 28. Okay, now what was our initial velocity? Well, it has to be 0, and we know that because right here it says it fell from rest. So we've got a 0 there. Now our time final, well, that was 3 seconds, 3.0 seconds. All right, and what was our initial time? Well, our initial time, we're just going to assume is 0 because that tells us that we have it just makes sense that when we start our timer that we're going to define that as 0 as our initial time. Okay, so this becomes negative 28 over 3.0. So we need 2 sig figs on our answer, so it becomes negative 9.3 meters per second squared. Okay, and that's the unit for acceleration. Interestingly enough, this ride does not fall as fast as gravity pulls us, and we'll learn that in a couple slides. All right, so when we're graphing velocity, put velocity in the y-axis, time in the x-axis. Now be careful, these look very, very, very similar to the position versus time graph, but they tell you very different things. All right. So the slope of velocity versus time graph is the acceleration. So if we want to find the acceleration of this object, all we have to do is find the slope of it, okay, or the rise over the run. And you'll notice that here, if we take the rise of this, that's really just the change in velocity, right? Because we're taking the final minus the initial, and then the run is just really the change in time. So notice that the slope correlates, rise over run correlates to the formula for acceleration that we already found, or that we've already worked with, okay? So the rise is velocity, the run is change in time, okay? And so in this graph, our velocity is constantly accelerating, right? Because at this moment here, our velocity is about 10 centimeters per second, right? At this, we're at about 20 centimeters per second, and we're just going to keep getting faster and faster and faster and faster, all right? And then if we're ever given a velocity versus time graph and we want to find the average velocity during a period of acceleration, so that means if you've got some acceleration and we want to find the average velocity within that time period, this is the formula you're going to use. You just simply take the velocity initial plus the final velocity over 2. Or you can do, you can flip them and always just do final first if that makes more sense to you. So final plus initial over 2. And really that's just finding the average. Okay. So let's take practice here. So we've got this train and it's moving, and this is the velocity, okay? Velocity versus time graph. And we want to decide what its motion is like at each of these points, A, B, and C. All right, so we've got velocity at time A, velocity, and we want to know its motion at A, B, and C. So at A, what's going on? Well, we see that our velocity is positive. How do we know that? Well, we assume that this is 0, right? We assume that this is 0 velocity and that up above here are positive. So we know we're going to the right. Okay. Now we have to decide if we're increasing or decreasing. Well, the best way to do this is to do like what we did when we talked about instantaneous velocity, and that's to draw a tangent line. So remember, we're going to draw a tangent line. All right, and you're going to see all my bad drawing skills here. We draw our tangent line that's going to touch our slope or our graph at one point, remember, so our tangent line. And so you see that our tangent line has a slope that's positive. So that means at point A, our train is moving to the right and it's increasing in speed. Okay, so it's accelerating to the right as it's going. Now at point B, you can see that we still have a positive velocity. We're going to the right still, but our tangent line is practically flat. Okay, and remember, if our slope is 0, remember slopes tell us what the acceleration is. So the acceleration, so our velocity is constant at B at some velocity to the right. We're going to the right and our acceleration is 0, so therefore our velocity is not changing. And then finally at value C, now this is where lots of people get fouled up a bit, is to, oh, I've got myself all confuzzled. So see, is there a line tool? Wouldn't it be awesome if there was a line tool? There's not, though. Okay, so at C, we've got our object, and it's going still positive, so that means it's going to the right. But we can see that on this really bad tangent line I drew, that now our velocity has a negative slope. So therefore that tells us that our acceleration is in the negative direction. So therefore we are slowing down. Now hypothetically, what if this line kept going here and we had a point D down here? Okay, so at point D, if we kept going, what would our line look like, or what would our motion look like? Well, notice that now we're below the 0 marker for our velocity. So which direction are we going? Okay, we're no longer going to the right because our velocity vector is now negative. Okay, we're now going to the left. So therefore, because it's negative, we're going to go to the left. And then our slope of our tangent line is still negative. So it's because our slope of our tangent line is negative, we're also going to the left. So that means we're going to be speeding up to the left. All right. Okay, kinematic formulas. Okay, so we get the kinematic formulas are these 4 special formulas that we're going to use to help us relate velocities, distance, time, and acceleration. Okay. And so here are what you want to know, all right? If you see a delta x, really that's talking about displacement. If you see vi, that's your initial velocity, final velocity is vf, and delta t is your time interval, and then a is equal to your acceleration, all right? So add this one to your notes, a equals acceleration. So here's your kinematic formulas. Pause the video, okay? Write these down right quick. Now the one thing that I want you to pay attention to when you look at these is notice, remember from before we had these 5 things we were working with, delta x, vi, vf, delta t, and acceleration. Notice that those 5 things never appear all together at once. Okay, in this formula we've got delta x, vi, vf, and delta t, but there's no acceleration. Okay, in this one we've got vf, vi, acceleration, time, but there's no delta x. In this one, we've got delta x, vi, delta t, acceleration, delta t, so there's no v final. Okay, so you can see in different cases, depending on what kind of things you know, you can use one of these formulas to solve for the other parts that you don't know. We'll do several practice problems about this here in a minute. Okay, so here's our first one. All right, so a bicyclist accelerates from 5 meters per second to 16 meters per second in 8 seconds, assuming uniform acceleration. So really that just means our a doesn't change, uniform acceleration. What distance does the bicyclist travel during this time? So here's what I want you to do. All right, as you're getting used to solving these problems, I want you to just go ahead and list out the things you know. We've got delta x, vi, vf, delta t, and acceleration. All right. So acceleration, so we've got delta x, says what distance, so that's what we're trying to find, so put a question mark next to that one because that's your unknown. Initial velocity, well it's accelerated from 5 meters per second, so it's 5.0 meters per second, all right, and our final velocity is the 16 meters per second, so we'll put that down, meters per second, and then our time is 8.0 seconds. Now, acceleration tells us it's constant acceleration, but it doesn't give us a value. So that's a good hint that we're probably not going to need to use acceleration. So we're going to look at these first 4, and we're going to say, all right, I've got vi, vf, and delta t, and I need delta x. So we need to pick one of our kinematic formulas that uses those 4, delta x, vi, vf, and delta t. All right. So it has to be the first one. Okay, it's because it gives us, we're trying to find delta x, and we have vi, vf, and delta t. So delta x equals 1/2 vi, so delta x is equal to 1/2 vi plus vf times delta t. Okay, now if for you that are paying attention, 1/2 vi plus vf should look very familiar. It's exactly the formula we had right here at the bottom right. Okay. So we're just taking the average velocity and multiplying it times time. Okay, so we're going to plug stuff in. We don't have to rearrange our question because what we're solving for is already on the equal side. That's not always the case. Okay, so 1/2 times our initial velocity, which is 5, and our final velocity, which is 16, times our delta t, which is 8. All right, so our delta x is equal to, we're going to plug this all into our calculator, 5 plus 16 times 4 is equal to 69. Okay, now what's our units going to be? Well, we could work through and make sure all our units cancel, or we could just assume that delta x is a distance, and this was in meters, so therefore our distance is going to be in meters. All right, so our bicyclist traveled 69 meters. 5 plus 16 times 8 divided by 2. All right, just want to make sure I did it right. Okay, let's try another one. So an aircraft has a landing speed of 83.9 meters per second. The landing area of an aircraft carrier is 195 meters long. What is the minimum uniform acceleration required for a safe landing? All right, so write out our guys. Here we got delta x, vi, vf, delta t, and acceleration. All right, so delta x, well, if we want a safe landing, that means we better stop before 195. So we'll go with 195 meters. All right, our vi is 83.9. meters per second, right? That's our initial. If we're landing, that must mean we need to come to a stop, so therefore our final needs to be 0 meters per second. Our delta t, they don't say anything about time, so that's a pretty good indication we don't need time. And our acceleration, it says what is the minimum uniform acceleration, so that's what we're trying to find, is that acceleration. So we need to find a formula that has delta x, vi, vf, and acceleration. All right, so let's go back. So delta x, vi, vf, and acceleration. So the only one, delta x, what was it? Delta x, vi, vf, and acceleration. So none of our formulas match that, huh? Unless I'm... All right. So we have to do 2 steps on this problem. This sucks. Okay, so we got to do 2 steps here. So the only formula we have, if we want to solve for acceleration, we need to have a delta t. Okay, we can't use this one yet because we don't have a delta t, right? But we could use that one if we could find delta t. So if we go back up to this first one here and use this to solve for delta t, then we'd be good. So let's rearrange this guy so we solve for delta t. So if we multiply it by half over, so we get 2 times delta x, and we divide it by what's here, so vi plus vf, okay, and that's going to equals delta t, right? So 2 delta x divided by vi plus vf equals delta t. So now we can use that formula to solve over here. So delta t is equal to 2 delta x over vi plus vf. All right. So 2 delta x, so 2 times 195 over our initial velocity, which was 83.9, and our final velocity, which is 0. Okay. So now we're just going to say 2 times 195 divided by 83.9, get 4.6484 seconds. All right, so that's our delta t. Now that we have a delta t, we can throw this guy in here, 4.6484. All right, so now we have a delta t, and we can use that to solve for our acceleration. So the easiest of all these, because all these other goobers have squares and stuff, we'll use this formula here. Vf equals vi plus a delta t. Okay, so, but we want to solve for acceleration, so maybe we'll go ahead and rearrange this using acceleration, right? Or solving for acceleration. So we'll subtract vi over, so we'll have vf minus vi, okay, is equal to acceleration times delta t, so we'll divide this by delta t, and we'll get acceleration. Wait a second, does that look familiar to you? It looks familiar to me. Vf minus vi is delta v. Delta t is delta t. Acceleration equals delta v over delta t. It's the same formula. Oh my gosh. Anyway, okay, so we're going to use that here. So acceleration equals delta v over delta t is equal to vf minus vi over tf minus ti, but we really don't need that. We just need this value here. So vf, well, that's 0. Our vi is 83.9, and then our delta t is the 4.6484. All right, so we'll take negative 83.9 divided by 4.6484, and you get negative 18.049221. So we got to think about our sig figs here. Both of our values from our original have 3, so therefore we'll round it to 3, so we get negative 18.0 meters per second or meters per second squared. All right. Cool. So free fall. All right, so we got free fall. We got a ball, and it begins at rest, and we drop. So we've got some ball here, and it's sitting on a ledge or whatever, and we kick it off, or we drop it, and it goes down this way, okay? And so we need to come up with a velocity time graph for this. So let's go ahead and graph this guy here. So we got velocity over here. We got time down here. So let's think about what's happening to our velocity. Okay, so our velocity began at 0. Okay, maybe I'll redraw this. We're going to move this line up, make it a little easier on ourselves. Okay, so our velocity began at 0. Let's see, I think I can change color. What color should we use? How about blue? Okay, so our velocity began at 0, so at time 0 our velocity is 0. Okay, and we don't really have specifics on anything, so we're just going to guesstimate what happens. So as we drop our ball, and what begins to happen to our ball? Well, it begins to fall. Okay, so that's going to tell us we're going to be a negative negative velocity, right? Because we're going down. Down is negative velocity, so we're going. Okay. But what happens? So gravity pulls down, and we're going to be moving. Gravity always pulls at a constant value. So what does that tell us about our velocity? Well, that tells us that our velocity is a negative acceleration, right? Because gravity pulls down. Not only that, but it's always going to pull down at the same rate. So therefore, because it always has the same rate, that means the slope of our velocity versus time graph is always the same, because the slope tells us the acceleration. Okay. Now, here's some things that you need to know about free fall as we keep going. Okay. In physics, we're just, at least at this level, we're going to ignore air resistance just to make our math a little easier. Okay. During free fall, we're going to assume that acceleration is constant the whole time. Pretty much this is true. Okay, so that's not much of an assumption. Now, we call the acceleration, when in free fall, acceleration due to gravity. Okay, and on Earth, this value is negative 9.81 meters per second squared. Okay, you might also see it referred to as AG for acceleration due to gravity, and you might also see it referred to as gravity. Okay. And we always put that negative sign to tell us that it's pointing down, all right? Okay, so let's think about this. So we've got a ball, okay, and we're going to throw it up and down again, and we're going to try to predict what's going to happen to my velocity and our acceleration. So remember, our velocity, if we're going up, that means we have a positive velocity. So when we throw the ball and it's halfway up, it's still going up. So that means our velocity has to be positive. But what about our acceleration? Well, acceleration is always pulling down, and so therefore acceleration has to be negative. All right. Now when we're at our peak, imagine throwing a ball. It goes up, and stops. Okay, stops right there. So what does our velocity have to be? Right at the peak for that instant in time. Well, at that instant in time, our velocity has to equal 0, right? Because we go up, pause, and then come back down. Okay, now what's the acceleration? Well, the acceleration has to be negative, right? Because it's gravity, it's pulling down. It's not going to suddenly start pulling up or some other which way. It's just always constantly pulling down. Okay, what about when we're halfway down? Well, we went up, and now we're coming down, and we're halfway down, and what happens? That's right. It's negative. Has to be, right? Because we're falling down. And our acceleration is also negative. Pretty easy stuff, right? So let's draw a velocity versus time graph with that information, all right? So we got this guy. We got our velocity. We've got our time, okay? We'll go back to red, ink color, red, okay? So now we're at red. So when we first throw our ball up, what's our velocity? Well, we just said our velocity is positive. Okay, so that means we're going to be at some positive value, all right? And then, why does it do that? All right, so we're up, positive velocity. Then halfway through, what's our velocity at? Well, our velocity is 0 halfway through. And then, what happens at the end? Oops, our velocity is negative, okay? So at the end, we're here, somewhere down here. So notice that, and our acceleration is constant, so what does that tell us about about the shape of our line? Well, because the acceleration is constant, that tells us that our slope didn't change, which told us that we had a straight line or a linear line. So here's my attempt at a linear line, okay, going this way. So we're just going to say I drew it over there this whole time. Anyway, so there's what the velocity versus time graph looks like for a parabolic object. So we throw it up, and it comes back down. That's what the velocity does, right? It started very fast, slowed down, stopped, and then it started speeding up as it fell back down. Okay, kind of bizarre, right? All right, so here we go. So we've got a ball that's thrown straight up into the air with an initial velocity of 25 meters per second. Okay, 25 meters per second. We want to create a table showing the ball's position, velocity, and acceleration for each second of the first 5 seconds. So I'm not going to draw out the whole table, but what we're going to do is we're going to just come up with what formulas you would have to use. So we want to come up with the velocity and acceleration at each second for the first 5 seconds. Okay, so this is just a kinematics problem. So, oh, and we want the position. So we have to find three things: position, velocity, and acceleration. All right. So, so remember, so we've got delta x, we've got vi, we've got vf, and we've got delta t, and we've got acceleration. Okay. Now delta x, that's what the thing we're going to solve for. So to solve for delta x, we're just going to use that first kinematics equation. Okay. Let's see this guy. Okay. Delta x equals 1/2 vi plus vf delta t. All right. But that's not really going to help us, right? Because in order to use this equation, we need to have final velocity. So that's not really going to do us any favors. So really, we have, if we use this equation here, do we have everything we need for delta x? Well, we have initial velocity because it told us we threw it 25 meters per second up. We've got our time because we're going to be measuring at each second that goes by. So the first time we run the equation, it will be with 1. Second time will be 2, then 3, then 4, then 5. Okay, then do we have acceleration? Well, we do because it's just on Earth, and we know that acceleration is equal to negative 9.81. Delta t, same thing. Okay, so for each time, we're just going to use this formula here. Okay, so delta x equals 1/2 or vi delta t plus 1/2 a delta t squared. Okay, so we're going to use this one to solve for delta x each time. All right, once we have delta x, then we can easily take this and plug it into the top one, okay, to solve for vf. And we have to rearrange this formula in order to solve for vf. Okay, or we could take this formula and we could plug it in here. We don't even need any of these to solve for v final. We just need vi, which we have, which is 25, and then we have our acceleration due to gravity, which is negative 9.81, and then we've got our change in time, which is our seconds. Okay, and then finally, to solve for the acceleration each second, well, this is just a silliness, right? Because the acceleration is constant because we're on Earth and we're talking about gravity. So the acceleration is always equal to negative 9.81. Okay, so if we look at a completed table, it'll look something like this. So what I want you to do is go ahead and skip back a couple of seconds and check and do some of these problems and see if you get the same values as I did when I did this. Okay, so our acceleration is always negative 9.81. Our velocity, notice our velocity is positive and big, but then somewhere between 2 and 3 we hit 0, right? Because we were positive and then we're negative. Okay, so we had to hit 0 somewhere in the middle of that. Okay, and then we're getting bigger and bigger negative values. Notice that the height of our ball is also following similar trajectory. Okay, at 20.1, okay, we're at 20.1 centimeters high. That's a long ways. And then we've got 30.4 and then 30.9. Okay, so somewhere between here and here, probably we hit the peak. Right? Maybe it was like 31 and change. Okay, and then we simply go down this way. Okay, for bonus points, okay, not real bonus points, try to figure out what was the max height. Okay, what was the max height of our ball during this up and down. Okay. Anyway, do some of those practice problems. You got a quiz coming up over part 3, and then you got a unit exam just around the corner. Let me know if you have any questions.